Hello again, everyone. This is the mission science briefing for the Orbiting Carbon Observatory-2. And here to talk about the science and the mission that's upcoming is Ken Jux, the OCO-2 program scientist from NASA headquarters. David Crisp, the OCO-2 science team leader from the Jet Propulsion Laboratory. And Anne-Marie Eldering, the OCO-2 Deputy Project Scientist from JPL. So we'll begin first with Ken Jux, the OCO-2 Program Scientist from NASA headquarters. Ken?
Thanks, George. So Dave, Anne-Marie, and I have the privilege to talk to you all about the scientific reasons why NASA is launching the Orbiting Carbon Observatory-2. Most of you know about NASA in our human spaceflight program because that gets a lot of press, but NASA has a strong and vibrant science program, and in particular we have a strong Earth science program, and OCO-2 is the next important piece in the Earth science program. So NASA's been doing Earth science observations for about 40 years now, back in the early days of NASA's history. And a lot of these early observations are trying to understand the Earth's atmosphere, weather systems, climate-type observations. And nowadays, NASA has expanded that program to do a lot more things. So we have a much more expansive satellite program now. We have a very expansive suborbital program. In particular, we use a lot of specially adapted airplanes to do scientific research. We do observations from the ground. And we have a very strong research program that's designed to take advantage of all of these observations to better understand the Earth's science system. So one of the early success stories that we had at NASA, in particular for Earth science, was to understand the ozone hole. NASA had observations up to observe ozone for a very long time, and when the ozone hole first started, they were observed both from the ground and from a satellite NASA had up called TOMS, which showed what the ozone hole was, and it gave us an idea that something important was happening, but we didn't know how to address it completely. So NASA organized quickly some field observations, both from the ground and from some of our specially adapted aircraft, to go and look at the ozone hole itself to try to figure that out. And when we combine the satellite data, these aircraft data, and the research program, scientists around the world were able to fully understand what was going on, and that led to some very important international agreements that led to the Montreal Protocol. So that's just one example of the type of stuff that we do in NASA's Earth Science program. So in order to really understand the Earth system, you need a lot of data because it's a very complicated and integrated system. So this first graphic will demonstrate that, how it works. So the Earth system, this kind of shows a lot of the pieces, and all of these pieces interact with one another. So we have the sun, which helps to drive the heating of the Earth. We have the atmosphere, which is an important part of integrating the sun's input. We've got the surface, which has oceans, it has trees, we have agriculture. All of these things interact with the atmosphere and with each other, and of course the ocean, which collects a lot of the heat eventually that comes from the sun. And then probably one of the more important things, especially in very recent history, are humans. We're a critical part now of the Earth climate system. And in order to understand all of these things, we need data that look at all of these pieces of the picture. So how does NASA do it? One of the most critical ways that we do that is with our satellite system. Betsy showed you a slide earlier, and I have a different animation I want to show up to show a lot of these satellites that we have orbiting up right now. So if you look at this graphic, you see a lot of satellites, and they're all in orbits specifically designed to maximize the science of these particular satellites. And if you look closely, you see a whole bunch of them that are in nearly the same orbit. If you look on the right side right now, they're all in nearly the same orbit, and that's this constellation that you heard earlier from Ralph called the A-Train. And I could go in to tell you what all of these satellites do. There's a lot of observations. Y'all get very critical pieces of information, but we don't have all day. So I'm not going to do that, but I will touch into a few important things about how we do that. So if you bring up the next still, which you saw earlier from Ralph in the A-Train, OCO-2 is going to be on the front edge of the A-Train, but all of these observations that you see flying with OCO-2 are going to be very important for understanding OCO-2, and OCO-2's data are going to be very important for understanding a lot of these other satellites. In particular, if you look at the Aqua satellite, which is 2 back, it gets some very important observations about weather, about what's going on the surface with trees, with the terrestrial biosphere, and with oceans. And combining those data with OCO-2 data can be very important. Those 2 satellites you see right after, CloudSat and Calypso, they actually have active light sources on there, and what they tell us about is what's going on with clouds and with aerosols in the system. Understanding the OCO-2 data to the precision that we need, having those data with it, it's going to be very important. And the last satellite you see there, the Aura satellite, which I also have the honor of being the program scientist for, some of its observations tell us a lot about air quality in the lowest part of the atmosphere. And a lot of what affects air quality in the lowest part of the atmosphere is combustion processes, the same processes that lead to humans' addition of CO2 in the atmosphere. So scientists are going to be combining those types of data as well to try to understand and advance our science. But one of the more critical parts of the science system that we really want to understand is the carbon cycle. And to do that, my colleague Dave is going to come up to you next and tell you about how OCO2's data are really going to help us to answer questions about the carbon cycle. So George.
Thanks, Ken. And now to David Crisp, the OCO2 science team leader from Jet Propulsion Laboratory. David?
Thank you much, George, and thank you much, Ken, for that excellent introduction. To understand the importance of the carbon cycle and the importance of the measurements that OCO2 will be making in the next few months, I'm going to have to bring you back to grade school, where your teacher explained to you that plants, all the green plants on Earth, absorb sunlight and carbon dioxide from the air to form all of their leaves and their stems and their roots. And during the spring and the summer, when they're growing really fast, if we bring up the first video, you'll see that they actually make changes that are quite dramatic. So once again, the trees absorb carbon dioxide and sunlight, and the graph they're showing shows actually that they also change the amount of carbon dioxide in the atmosphere. When they're growing quickly, they take so much carbon dioxide out that we can actually measure it from ground-based stations here on Earth. We now have about 150 stations that are measuring carbon dioxide very, very precisely from the surface of the Earth. And what we see is during the spring and the summer, we actually see the carbon dioxide abundance of the atmosphere decrease by a couple of percent. In these measurements seen here from Mauna Loa, Hawaii. During the fall and the winter, when the trees lose their leaves and they decay, they release most of that carbon dioxide back to the system. Now, this cycle that goes on every year has been going on for thousands to millions of years. Now, you might also notice, though, that in addition to the up and down motion that we see as the trees breathe in carbon dioxide and re-release it to the air, you see that the curve is going up a little bit and to the right. Well, that's us. Human beings, as Ken mentioned, are now a major component of our environment and all of these cycles, including the global carbon cycle. Scientists measure carbon dioxide in units of parts per million, and what that really just means is that as you see here, and the 390 indicates that about 390 molecules out of every million molecules of air are actually carbon dioxide molecules. So we refer to that as a 390 part per million carbon dioxide ratio. Earlier this year, the amount of carbon dioxide in our atmosphere actually hit about 400 parts per million for the second time, it turned out, in the last 100,000 years, or I should say 800,000 years or longer. This is the highest level we've seen carbon dioxide in our atmosphere in a very, very long time. And once again, it's largely because of our contributions to the system. Now, to understand that system a little bit more and understand the carbon cycle and the kinds of measurements and the value of the measurements that OCO will be making, let's introduce some of the characters in the carbon cycle. You've already seen the land plants. So if we bring up the next graphic, the main players in this system include the plants on land. The next, of course, are the ocean. The ocean actually plays a major role in the carbon cycle, taking up carbon dioxide in parts of the atmosphere, or in parts of the world where it's usually colder, and then releasing it in places where there's upwelling and it's warmer. Then finally the atmosphere, which is the exchange media where they exchange carbon dioxide. The Earth's plants emit about 440 billion tons of carbon dioxide to the air every year, and then reabsorb a little bit more than that. The ocean also is a major player, emitting about 330 billion tons of carbon dioxide into the atmosphere every year and reabsorbing a comparable amount. The new players on the block are us. since the beginning of the industrial age, we've been burning fossil fuels, also practicing deforestation and other things that have been emitting carbon dioxide into the atmosphere at an ever-growing rate. Human beings are now emitting about 40 billion tons of carbon dioxide into the atmosphere every year. That's about 5.5 tons for every man, woman, and child on the Earth. And that as you can see from the graphic here, that input into the atmosphere isn't balanced by an uptake like the oceans and the atmosphere. So we're basically building up the carbon dioxide in the atmosphere of the Earth slowly, but at a ever increasing rate. So now, but that's just part of the story. The other part of the story, and the real mystery, is shown in the next graphic. We've been slowly but surely increasing the inputs of carbon dioxide by burning fossil fuels over time, and this is a graph that shows a number of tons of carbon dioxide that we've added to the atmosphere since about 1960. That's total emissions shown there, and you see it's going up to the right. We're now emitting about 40 billion tons of carbon dioxide. But that's only half the story, because it turns out that not all of that carbon dioxide is staying in the atmosphere. Only about half of it is staying in the atmosphere over time. The blue curve shows the amount of accumulation of carbon dioxide in the atmosphere every year. And it's only at about half the level we're putting it in. Half of the carbon dioxide we're dumping into the atmosphere every year is disappearing somewhere. It's dissolving in the ocean waters. About a quarter of it is. We know that from our measurements. And the other quarter we assume is going somewhere into the land biosphere somewhere, into forests, into trees, into grasslands, somewhere. But we don't know where. Have you seen a new rainforest spring into existence over the last, say, 40 years or so? Neither have we. We're looking for those kinds of processes because we know that that's what's going on that's absorbing this carbon dioxide. It is absolutely critical that we learn what processes are absorbing carbon dioxide in our system today, over half of the carbon dioxide we're emitting, because we need to understand, first of all, how much longer they might continue to do us that great favor. The other thing, though, is, as you might have noticed in that previous curve, is that while our inputs have been growing slowly and steadily over time, the amount that stays in the atmosphere varies dramatically from year to year. Sometimes almost 100% of the carbon dioxide we put into the atmosphere stays there, sometimes almost none. We don't know why. We need to understand those processes as well in order to understand how carbon dioxide will build up in our system in the future and how we might manage carbon dioxide buildup if that's what our policymakers decide to do. But we need to understand that. And to understand that, we can't do it with just 150 stations making precise measurements on the surface of the Earth. We now have a satellite that you heard about earlier, the Japanese greenhouse gases observing satellite, that has been making measurements for about 5 years. It makes another 350 to 1,000 measurements over the Earth every day. That still isn't enough to find the sources emitting carbon dioxide into the air and the natural processes that are absorbing carbon dioxide out of the atmosphere. We need far more measurements. So just like for weather satellites and weather measurements that we're making that have revolutionized our ability to predict the weather, we need satellites in space to make very much larger number of measurements at much higher resolution over the entire globe in order to actually start studying these problems. The Orbiting Carbon Observatory-2 is the first satellite that NASA has built that can do this. It will actually increase by something like a factor of 100 the number of measurements we make over the Earth every day. And so what I'll do is my colleague Anne-Marie Eldering will talk a little bit more about that later. But George, I want to give this back to you.
All right. Thank you, David. And Anne-Marie Eldering is our OCO-2 Deputy Project Scientist. Anne-Marie.
All right. Thank you, George. So Dave told you a bit about the carbon cycle and the mysteries that we want to solve with OCO-2. But how well do we have to measure carbon dioxide to answer these questions that he's posed? Well, he mentioned that the concentrations have reached up to 400 parts per million these days. And if OCO-2 wants to understand where that carbon comes and goes, we need to measure to 1 part per million. So that's really a very small change in that 400. And to give you some sense of that, we made a little jar of beans, and these represent 400 parts per million. If I look through the atmosphere, these might be all the carbon dioxide I see when there's 400 parts per million. So if I want to add 1 part per million, I just add a few beans here, and there we go. The concentration just changed by 1 part per million. That's what I have to see happen, just those few little beans. Where am I? Here we go, with OCO-2. So a little more information about why 1 part per million is so important. We made a movie that they'll show here of a carbon dioxide field that was generated by a model. Our colleague Leslie Ott at Goddard Space Science Center made this movie of the total column of carbon dioxide. This is the type of information OCO-2 will collect. And you can see the colors here range from deep blues, which are 370 parts per million, to these reds that are 390. But if you look at some of the details, the northern hemispheres are kind of a blue down to a moderate red in the more southern hemisphere. That's only a 10 part per million difference between the northern parts of the globe and the southern. And if I'm trying to answer the question of whether the carbon dioxide is being taken up by the northern hemisphere or the forest over Asia, you can see those differences are just small. There may be 1, 2, or 3 parts per million of difference in the concentrations of carbon dioxide. So OCO2 is really required to have a high degree of sensitivity to make carbon dioxide measurements to see these differences across the globe. And you see the features Dave talked about, how the northern hemisphere is very blue or low in concentration because the trees are growing and taking up the carbon dioxide. There's areas of red where we're burning burning biomass, trees, forest fires create these big carbon dioxide concentrations. So that's what we expect to have to sense with the OCO2 instrument. So it's a challenging measurement, and I want to tell you just a little bit more about how we do this. So the OCO2 instrument is actually looking at reflected sunlight. We have a still graphic here just to illustrate the idea. Oh, sorry, that's not quite it. But you can imagine the sun's shining, reflecting off of the Earth's surface, and then back up to our instrument. And that's the light that we receive to make these measurements. We actually split that into 1,000 small fractions of a wavelength of light in 3 different bands to see the unique fingerprint of the absorption of carbon dioxide. So we believe we have an instrument that's built. It includes the technology we need to make this very precise measurement of carbon dioxide. And there's been a new interesting discovery. Researchers have recently been looking at the unique fingerprints of light, and in a number of remote sensing measurements, including GOSAT, they've noticed that they see something we hadn't looked at before. And as Dave mentioned, plants are a really important part of the carbon cycle. And in fact, when those plants are doing photosynthesis, they actually give off a little bit of light. They fluoresce or emit light. And researchers have now shown that they can detect this signal in remote sensing measurements. So the final figure I wanted to show you is a simulation of the expected signal we should see from these plants doing fluorescence, or the solar-induced fluorescence. This is a map of what OCO2 is expected to observe. And this will be really valuable because the carbon dioxide measurements are the key to unlocking the sources and sinks, but additional information like the fluorescence from the plants that are photosynthesizing gives you another piece of information to help unlock that puzzle and figure out what's happening with the carbon cycle. So I think I speak on the behalf of the team. We're just incredibly excited about our launch. We're glad the weather's looking good. Everything's a go for 2:56 a.m. on the 1st. And we think that the OCO2 measurements should have the precision, the coverage, and the resolution that we need to really answer this important science question about the sources and sinks across the globe. Thanks. Back to you, George.
Thanks, Anne Marie. And we're ready now to take questions. And once again, you can ask questions on Twitter by going to #AskNASA during this briefing and question and answer session. We'll start here in the room, and then we'll take any Twitter questions. Justin.
Justin Ray with spaceflightnow.com. For David Crisp, you were obviously involved in OCO-1, the first go-around. What's it like to be back here 5 years later?
It's absolutely fantastic to get another opportunity to actually conduct these incredibly important scientific measurements. It's been a long, hard road, but boy, I'm glad to be back.
Janine?
Considering the past experience, how nervous are you for Tuesday morning? Are you lots of stomach medicine?
Actually, we've done everything humanly possible this time, as before, to ensure a safe and successful launch. In addition to that, the launch vehicle that we're riding on this time, the Delta II, is the most reliable launch vehicle in NASA's fleet. I am honored that anybody would consider flying such a small science experiment on such a highly reliable vehicle. So I'm looking forward to getting past this step. As I mentioned before, it's been a long run up to the starting line of this race. But we're ready to start now. And so most of us are looking forward, planning ahead. We've had opportunities working with the Japanese over the last 5 years on the GOSAT mission, analyzing their data, that have been absolutely fantastic. We've learned so much about what we can learn about these data, learn about CO2 from space-based data. With OCO-2 taking about 100 times as much data each day as GOSAT, we're really enthusiastic and looking forward to the kinds of things we might learn from these data.
What kind of tweaks were you able to make to get better data and better take advantage of the extra time?
Can say something about what we've...
As Ralph said earlier, as Ralph Basilio mentioned, this is truly a carbon copy of the OCO satellite, and we basically used the plans we had last time because it was seen as being the fastest and lowest risks and lowest cost method to get these critical measurements made. So it turns out that, as Ralph did mention, we also we couldn't find all the parts we used to build the original spacecraft. Some of them were obsolete. It's been almost a decade and a half since we started this mission, and so we did have to replace some parts that had become obsolete or otherwise impossible to get. But in replacing those parts, we basically tried to duplicate the functionality of the original parts so that we could meet our requirements. The two different systems essentially try to meet the same set of requirements.
Okay, Justin had a follow-up.
Yeah, for any of the participants, the mission is 2 years for a nominal mission, but how long do you expect the mission really to last?
I'll take that one. A lot of this will depend on how long each single string part of the instrument actually lasts. NASA's history is these types of missions last a lot longer than they were planned for, and we're hopeful that that happens. There's the one time constraint is the amount of fuel that the spacecraft actually carries. It should take us up to a decade. We think that this instrument could stay up for with that one time constraint. All the other single string components we don't know, but history, and with us as careful as the team has been, we hope that they all last at least that long.
Thank you for a very informative presentation, and I am very curious. You touched on the mystery of disappearing accident outside, and I am curious, do you have any suspicion where it's disappearing, and will you share with us if you discover it?
As you know, scientists usually have a working hypothesis, but what we're trying to do usually is to break that hypothesis. And so I could be 100% wrong here, but here we go. We know that the ocean is taking up about 1/4 of all of the carbon dioxide that we're emitting at this point. And we know that by measuring the pH, or the acidity of the ocean water, and watching it increase over time. The rest must be going into the land somewhere, but we don't know whether it's the rainforest like the Amazon in the tropics, or mid-latitude rainforest like those in Oregon, or forest like those in at very high latitudes, the boreal forest. It can be in any of those areas, and there are very good theories supporting all three. And about every year, scientists put a paper in Science magazine or Nature proving that it's one of those three, but it's different every year. We're hoping to finally be able to discriminate between those different possibilities with OCO-2.
Last thing, it's wonderful to see a woman as a part of such an accomplished team.
We agree.
Yes.
Truly. How many women are empowering this incredible group?
Well, it's interesting because actually in atmospheric sciences, there's a good representation of women in those fields. And so we actually have the movie I showed you was made by one of our female colleagues over at Goddard. And I would say it's a fair reflection of the graduation rates and the training that's happening these days. So it's a nice environment for me to work in. I like it.
Steve, we got questions on Twitter.
Yeah, several from social media, George. First one, how long will it take for OCO-2 to observe the entire planet?
16 days. We don't cover the entire planet. OCO-2 makes measurements along a narrow measurement track and it basically circles the Earth every 100 minutes or 98.9 minutes. And so we never actually map up the entire planet, but we do repeat our track about every 16 days, and the largest distance between the tracks at the equator is about 152 kilometers or about 100 miles. And each track is about 10 miles wide at the most, or 7 miles wide at the most. So it takes us, we cover 7% of the Earth every repeat cycle, every 16 days.
Okay, the next question. The OCO-2 mission, I understand, will be used to identify where on Earth CO2 is being absorbed from the atmosphere, the carbon sinks. How will OCO-2 data help figure out whether these sinks will continue acting as sinks into the future?
Thanks, Dave. So one important thing to realize is that the measurements we make don't alone answer this question, but we actually work with the science community and groups of science, of modelers who have representation of all these processes around the globe. And our thinking is that when we have this observational data, they work with their global models, they can basically test their hypotheses about what's driving the change over time and over space. So the more we understand what the key drivers is, perhaps it's water availability, perhaps it's sunlight, perhaps it's other constraints, then we can improve the way they represent those models and therefore improve the predictions of the future. So it's a multi-step process to get to those predictions, but we can see the path there.
Okay, next question. How will OCO-2 data be used by environmental scientists to tackle pollution, the pollution caused by emissions of greenhouse gases?
Okay, I'll take that one. What we will be able to see with the OCO-2 data are areas of the globe where there are more elevated levels relative to areas nearby. So that's one way that people will be able to use these data to try to understand pollution sources. But we also have a number of other observations that tell us about what's going on with pollution as well. And there's different types of pollution in the atmosphere, and they all come from different types of sources. So scientists, by taking these combined sets of data, they'll be able to get a much better picture of what's going on with the emission sources that lead to pollution.
A question from Ustream. Will NASA use OCO-2 data to generate images of global CO2 concentrations that will be released to the public?
So we have a group we are working with and a simple website, co2.jpl.nasa.gov, where we'll be sharing this information. And one of the plans is to make images, as they ask, of the monthly concentrations of carbon dioxide. But as Dave mentioned, we don't see every location on the Earth, so there will be some interpolation or averaging that we have to do to make these maps. But you should find those up on our website, say 2015, when the data is ready to go.
Another question